Let's talk about the periodic trends. So I already have a video on basically all of them. Yeah, all of them. I have atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. But in this video, if you're in a rush, I'm going to just summarize them all really quickly without going into too many caveats and whatnot. So let's run through them. Speed mode, learning all the periodic trends, okay? So the first one we're going to talk about is atomic radius. And so this, if you understand this one, all the other ones make sense. And so atomic radius is just saying how big are the atoms, right? What's the distance from the nucleus to the outer rim of the electron cloud, right? And so if we look at the periodic table, as we go down a group, of course, the atoms are getting larger, right? We have more protons, which is the atomic number is the number of protons. We're going to be adding more neutrons naturally. And then, of course, we're adding more electrons. So it makes sense that the atoms are getting larger. But now, why are they getting larger? Like, to be more specific, it's because each period number corresponds to a principal energy level of electrons, or an electron shell. And I have a video on atomic orbitals where I talk about this. Also, electron configurations kind of talks about this as well. So as we go down, each period is adding a new electron shell. So it's just like adding, if we have an atom, let's just say we got some protons in here, and we have an electron shell like this. We have our electrons in there. Now we add another electron shell. Well, it's going to be significantly larger, and now we're adding more electrons in here, right? Let's just give this 3 pluses to make this make sense. And so as we go down the group, it's very obvious that the atoms get larger. Now, as we go to the right, the atomic number also increases, right? I mean, if we start over here, potassium's 19, krypton's 36, it's in the same period. So you would think that the atoms get larger again, but it's not true. What actually happens is we're in the same principal energy level here, or we have the same valence shell, electron shell, right? Which is shell 4, period 4, shell 4 is the valence shell, which means the outermost shell. So as we go to the right, we're not adding new shells of electrons, we're just adding more electrons to the outermost shell, but we're also, of course, adding protons to the nucleus. And that increased nuclear charge is going to pull those electrons in more tightly and actually make the atoms decrease in radius as we go to the right in general, okay? All these things I'm saying are in general. There are some caveats here and there, or exceptions rather. But in general, what you have to know in general chemistry is that the atomic radius increases down and it gets smaller to the right. So just to put that simply, atomic radius gets larger down and to the left. Now, so let's do that up here. Let's go over like this. We're going to go over here like this, and we're going to say radius is larger. Okay, now that's atomic radius. Ionic radius, I'm going to run through this really quickly. If we, and knowing electron configurations is really going to help, so if you check out my video on that, this will all make a lot of sense. But let's say that we are sodium right now. We are in shell 3. We have 1 electron in shell 3. If we take away that 1 electron, we now have the electron configuration of neon. So we just wiped out our outermost shell, the valence shell. And now we only have, this is in period 2, so there's 2 electron shells here. So we just made it smaller. But it's not neon, it has an extra proton. So whatever size neon is, it's going to be even smaller because we have a more highly positively charged nucleus. So it's going to be pulling those electrons even tighter, okay? So being a positive ion, a cation, makes it smaller. The more positive, the smaller it gets. When you get enough positive charges to wipe out the principal energy level and get over to the noble gas configuration, it gets dramatically smaller. And then the opposite is true. If you're adding electrons and you're making it negative, it's going to get larger, because let's say we have fluorine here. We add an electron. Now it has the electron configuration of neon, but it only has the 9 protons. So it's not able to hold on to them as well. And so there's going to be some electron repulsion, and it's going to get larger. So negative ions have a larger radius. Positive ions have a smaller radius compared to the original atom, okay? Now, let's talk about ionization energy. And actually, let's just write a little something over here. So let's just say positive ions get smaller and negative ions get larger. Okay. Now, let's talk about ionization energy, right? What is ionization energy? Ionization energy is the quantity of energy required to remove an electron from an element in its gas phase when all the electrons are in the ground state. So just to make that simple, it's how much energy is required to remove an electron from an atom with some extra fine print, right? So we take an element and then we're going to add energy to it, and we're going to get the element that's now positive and an electron. We're separating it, right? The electron is a product here because we're ripping it off. How much energy is required to do that? Well, to make it simple, let's think about our first periodic trend. The atoms get larger down to the left. So if you have a larger atom, the electron is further away from the positive nucleus, so it's going to take less energy to pluck it off than if the electron is right next to that positive nucleus, and now it's like a North Pole and a South Pole magnet being close to each other. It's harder to rip them away. So ionization energy is going to have the inverse relationship to atomic radius in general, so it's going to increase up and to the right. So if we go over here, and I'm going to go to the right, and then I guess I'll just have to do this because I didn't leave myself enough room. I'm going to go over here, and I'm going to say ionization energy. It's increasing, right? Now let's talk about electron affinity. Electron affinity is basically this, but in reverse. So if we take an atom and we give it an electron, and now we have a negative anion here, right? How much energy is released when we do this? Okay, so this one over here was ionization energy. This one is electron affinity. And so it's just how much energy is released when you give an element an electron. And so if we think about it, it's kind of the opposite of ionization energy. If something does not take much energy to pluck an electron off, that's saying that it doesn't really want electrons that much, right? So you're not going to release a whole bunch of energy by giving it an extra electron. They don't really want it anyways. The electrons are pretty far from the nucleus. So in other words, down here where we have a small ionization energy, we're also going to have a low electron affinity. And then the same thing is true. As we go up into the right, how much energy is required to take an electron away from the atom? If it's a lot of energy to rip an electron off the atom, well then it would be happy to get an electron, right? So electron affinity is going to increase up and to the right. In general, there are some exceptions. Group 2A and group 5A are the two big exceptions that you should know about. In other words, the electron affinity increases up and to the right, but from whatever element you're at, when you get to group 2A, it goes down a bit, and then it continues with the trend. As you go to the right, it increases, and then you get to group 5A and you get like another dip. So that's electron affinity. So let's put that over here. Electron affinity. And now let's talk about electronegativity. Electronegativity is a measure of how strongly an atom attracts electrons in a chemical bond. So it's going to be the same idea again, essentially. Now, electronegativity is just a scale, okay? So like basically like a GPA is 0 through 4.0. Electronegativity is the same idea. 4.0 is the max, okay? And so it's not like something that you measure. It's a scale that relies on things like bond enthalpies, ionization energy, electron affinity, and the trend is going to be the same. As we go and we have a higher ionization energy and a higher electron affinity, that means that the atom wants electrons, right? The higher ionization energy means it's harder to take an electron away from it, and the higher electron affinity means it releases energy, which is like beneficial and it's more stable, right? When it gets an electron. So as we go up and to the right, the atoms want electrons, as if we want to personify them, and so electronegativity increases up and to the right. Again, it all goes back down to atomic radius if we want to simplify things and think about it that way. And so electronegativity also increases up and to the right. I'm going to say increases. This is increases. All right. And those are the periodic trends, guys. If this helped, please give a like, follow, share, save. Check me out in all these locations. And if you patronize me over here, that helps me to continue making these videos for free. Thanks for watching. I'll see you in the next one.